The last topic in our discussion of vectors will be relative motion. So, how things appear when they're moving depends on the point of view or the frame of reference from which it is being observed. So, if you're standing on the road looking at a car coming at you, it looks different than if you are in another car moving and observing that car coming at you. Or viewing something being dropped from a plane while you're standing on the ground, or if you're actually in the plane observing the object being dropped from the plane. Makes a big difference. So as for instance, you're meeting another car head on, both speedometers read 50 miles an hour. How do you see the other car approaching you? You're in a car moving 50, the other car is moving 50, both coming at you. You are observing the other car coming at you at 100 miles per hour. So that probably is fairly intuitive, maybe not, but if you think about it, the gap between the two cars is closing at a rate of 100 miles an hour. And from your point of view, you're just kind of, if you don't look at the trees zipping by from your motion, you might think you're at rest and that other car is coming at you at 100 miles an hour. Well, what if both cars were instead moving perpendicular to each other or some other angle that's not directly in line with each other? Then you can find the relative velocity using vectors. So let's look at a case in point. Here we have velocity of car 1 with respect to the road. Here is a vector corresponding to its speed and direction. And then we have another vector which corresponds to the motion of the second car. So velocity of car 2 with respect to the road. So just to clarify what these vectors with their subscripts mean, v car 1 slash road, the velocity of car 1 with respect to the road is what that means. The first subscript is the object being observed. You're observing car 1. From what point of view are you observing car 1? The road. So that's what that means. So this motion is what you would see car 1 doing if you're standing on the road watching it. Now, even though you see this vector going up, this one going to the right, you don't get confused that, here it is, there's a piece of paper, say, with these vectors drawn on them. Doesn't mean this is vertically up. Looking at this screen, yes, it is. But maybe you want to consider these vectors from the point of view of looking at them from above. So we've got a top view looking down on them. And then maybe this one is north and this one is east. How does that sound? You're looking from above. This is north and east. But they represent the motion while you're standing on the road. So if you were standing on the road, we'd see the top of your head here, and there's the motion of the car. Okay, now I want to consider how to find the velocity of car 2, not from the point of view of the road, which is this magenta vector, but from the point of view of car 1. So you're in car 1 doing this motion, and you're going to observe what it looks like to see car 2. Well, there's a certain convention to understand that. We write the vectors in a particular way, and it will reveal the answer. So here's how you write the vectors to describe the situation. The velocity of car 2 with respect to car 1, again, that's how you say this, car 2 slash car 1 is with respect to or from the point of view of car number 1 is, let me just write it out, velocity of car 2 with respect to the road plus velocity of the road with respect to car 1. Say what? Well, there's really a simple method of doing this. See that first subscript, car 2? Well, when you, on the other side of the equal sign, you start with that same subscript, car 2. And at the end of this whole thing, we have car 1, and it will be seen at the very end. So car 2, car 1, car 2, car 1. And what's in the middle? What's in the middle is the road, kind of almost like a placeholder, you could think of it as. It's a common reference that ties them together. So notice that the outer subscripts are equal, and that will always be true if the equation is correctly written. Now, what would be this idea of the velocity of the road with respect to car 1? You may notice that this is a reversal of the subscripts from the original scenario of velocity of car 1 with respect to the road. You might have guessed it is simply the same size of vector, but the arrow is in the opposite direction. So really, it's what the road is doing from the point of view of car 1. If the car is going up the road, if the car is, say, okay, I'll just use the word up. If the car is going up like this, the road looks like it's going the other way. So the road goes in the opposite direction of your motion. Hopefully that makes sense. So this is the velocity of the road with respect to car 1. So it's the negative of the motion of the car with respect to the road. You're sitting in car 1 looking at the road. There, have I said that enough? So we're ready to add the vectors to determine the result. Velocity of car 2, car 1. Well, we already know what this one is. We've seen it explicitly. And so we're just going to add vectors. So there's the velocity of car 2 with respect to the road. Hasn't changed. And we're going to add, you know how to add vectors now, tail to tip, the road with respect to car 1 vector. There it is. And that's it. Let's just draw the resultant in. Here's the resultant. And we should have our answer, which might match your intuition when you realize that car 1 is moving up. So because of that, the road looks like it's going backwards. But let's just, all right, let me discuss it in terms of car 2, because we're looking at the motion of car 2 from the point of view of car 1. Because of car 1's motion up, that alone would make car 2 move down, or appear to move down the opposite way if car 2 is just sitting there. So car 2 looks like it's going the other direction that we're going, which is down. But car 2 is also moving to the right, so we just leave that alone. We have a right motion and a down motion, and that results in this down and to the right diagonal. So maybe now it matches your intuition.